In this video, we're going to talk about pH curves for titrations. We're going to look at the titration of a strong acid and strong base, a weak acid with a strong base, and a weak base with a strong acid. We're going to look at where their equivalence points fall on the pH scale and why that's the case. The first one we're going to look at is hydrochloric acid with sodium hydroxide. So you have a strong acid and a strong base. And what you'll notice is that there's not much of a change in the pH as you're adding the base until you reach the equivalence point, at which point the pH skyrockets. That has to do with the fact that pH is a logarithmic scale, and only right around here will you notice that any amount of hydronium ion that's in there relative to the concentration, especially since it's 1 molar, is going to make the pH really low. But once you neutralize it and you get really close to that equivalence point, the pH is going to skyrocket because you're using up all the hydronium ion. Then what's going to happen, once you reach the equivalence point, any additional base being added is going to result in a hydroxide ion buildup, which is going to make the pH skyrocket. So you have a very small slope here, and you have a shoots up, and then because it's a logarithmic scale, once it reaches a certain point, the additional base is only changing this pH so much. So again, strong acid, strong base, you have an equivalence point of right at 7. And that's because when you neutralize the acid with the base, your products are going to be a salt and water. And the salt's not really going to have any component that's going to act as really a strong acid or a strong base and have any impact on the pH by producing more hydronium or hydroxide ions. The next one we're going to look at is the titration between a weak acid, acetic acid, the one we use in the lab, and a strong base. And you'll see that the pH curve looks quite a bit different. You'll see that the slope here is actually fairly noticeable relative to that of a strong acid and strong base, which would be right around here. Yes, that was an eraser. Okay. The reason for that is because as you're adding the base, you're going to produce the acetate ion. So the conjugate base of the acid in this case is actually a relatively strong base. It's capable of removing a hydrogen from water and resulting in the production of hydroxide, which is going to make the pH go up. So as you're neutralizing it, the species that you're generating is going to act somewhat basic, and it's going to cause the pH to go up. Also, when you get to the equivalence point and you have none of this left and it's all in the acetate form, you're going to have water in the acetate, and you're going to have basically a basic solution because you're going to have the hydroxide ions being produced. So equivalence point when you have a weak acid being titrated by a strong base, the equivalence point is going to be north of 7. All right? And depending on how weak the acid is, that'll determine where it actually falls in that range. But you can see that two differences. The slope is quite a bit more because the conjugate base is going to actually produce hydroxide ions and increase your pH. And your equivalence point is going to be north of 7. In the titration of a weak base with a strong acid, obviously it's going to be flipped because the solution initially is going to be all base, all about the base, and it's going to have a high pH. So as you're titrating it, you're going to notice the pH goes down, right? And this slope is still a little bit steeper than that of a strong and a strong titration, but you'll notice that at the equivalence point, your pH is less than 7. And that's because, in the example here, ammonia, when you react that with hydrochloric acid, you make the ammonium ion and chloride. This is a really, really weak base. Doesn't really do anything. This right here is actually a relatively strong conjugate acid that's capable of donating a hydrogen to the solution. If you have something donating a hydrogen ion in the solution, it increases the hydronium ion concentration, and your pH is going to drop. So that's why the equivalence point with a weak base and a strong acid is going to be less than 7. And the last titration I want to show is the titration of a weak diprotic acid. Diprotic meaning it's capable of donating 2 hydrogens. We have oxalic acid here, which we use in the lab. And at first, when you're titrating it, you're going to essentially be converting the oxalic acid into its conjugate base, but its conjugate base is still acidic. It has a hydrogen it's capable of donating to the solution. So what you really have is 2 equivalence points. The first one, which is this little point of inflection, is when you've converted all of this into its conjugate base. And then you have a second equivalence point where all of this is getting converted into the oxalate ion. So 2 equivalence points, and that's where it's interconverting between the diprotic form to the monoprotic form to just the anion. We'll also notice that because this is a weak acid, it's going to have an equivalence point north of 7. Because this conjugate base right here it still has the capability of removing hydrogen from water and resulting in the formation of hydroxide ions in solution, thus upping the pH. So we've looked at 4 different titration curves, and we've kind of analyzed the components of them.